Okay, so we're going to talk about finding, on the topic of graph algorithms, finding a minimum spanning tree of a graph. So it might be good to first define what a tree is. So for example, if we had a graph like this graph, this would be considered a tree by definition in computer science. A tree is any graph that has all of its components connected to each other, but there's no cycle in the graph. And it's typically drawn as, like a binary tree with one node as the root, and then maybe it has children under it, and then grandchildren, and so on. So they refer to it as a tree, but it's more like a bush, like an upside down bush, but they call it a tree. So, but anyway, so this would be an example of a tree. Every vertex is connected to each other, and there's no cycles in it. This is an example of a graph that's not a tree, which is really the same graph except with this one extra edge added. But what this does is now creates a cycle in the graph, and that makes it not a tree. And if we had a graph that had a collection of trees, a bunch of trees, separate, sometimes those are referred to as a forest. A forest, a collection of trees. Okay. A spanning tree of a graph that is not a tree. So for example, if we had this graph, this was our graph, and these vertices are all connected to each other. Here's an example of a spanning tree of that graph. What a spanning tree is a subset of the graph, a subset of the edges. Same vertices, but with a subset, so E prime we're going to say is a subset of the edges, such that the resulting graph is a tree, and all the vertices are somehow connected to each other. So we could argue that this vertex and this vertex are connected to each other. It has to take a pretty long path to get there, but they are connected. So you might be interested in finding out a spanning tree of a network. Is, let's say these are a connection of nodes, and you wanted to make sure that they're all connected in case one link went down. You want to make sure that there's some backup to them, so you would need a spanning tree to make sure all the vertices are connected to each other. Okay, so now the question is, how many spanning trees can a graph have? And the answer is going to be a lot of spanning trees. So here's a simple example. We have this graph, 4 vertices, kind of forming a box, and we have 4 different spanning trees for it. So this is, again, not a tree because this is a cycle. Here's one example of the spanning tree. Here's another one. Here's a third one. And here's the 4th one. So this graph right here has 4 spanning trees. So just as a kind of a, we could maybe think back to some graph theory, but if you had a cycle with 4 edges on it, how many spanning trees could that generate? Just if you had a 4 cycle, obviously if we take out any one of these edges, the cycle goes away, leaving you with a spanning tree. So for every edge on the cycle, you have that many spanning trees for that cycle. If you had a graph that had a collection of cycles, they'd stop multiplying. So could have many, many spanning trees for a graph. So now there's a question of a special type of spanning tree, which is the minimum spanning tree. Out of all the spanning trees that a graph could have, if the edges have weights assigned to them, you want to find a spanning tree, but one that has a total weight less than all other spanning trees. So for example, if we had this rectangle, and the weight here is 1 and 1, and the weight on the sides of 2 and 2, like we said before, this has 4 spanning trees, but it has 2 minimum spanning trees. So we obviously want to get rid of one of these edges to get a spanning tree. And we want a minimum one, which means we want to get rid of one that has the weight of 2. So this is one example of a minimum spanning tree of this graph, and here's another minimum spanning tree of this graph. Okay, so if you were interested in finding a spanning tree, not necessarily the minimum spanning tree, all you have to do is take a graph and run one of your search algorithms like breadth first search or depth first search on the graph. And if you remember when breadth first search and depth first search are running, sometimes it visits a vertex that's already been visited. That would mean you found a cycle. Don't include that one. think in our textbook, it would be an edge that was turned gray. And if you visit an edge that's turned gray, just ignore it. And just print out, or just keep all the edges that you visit that have not been visited before. You will visit them in a tree order. Breadth first search and depth first search might give two different answers for a spanning tree. But that's okay, if you're just looking for a spanning tree and not necessarily a minimum spanning tree, those algorithms work fine. So if our goal is to find a minimum spanning tree, that would be a spanning tree that would be all the vertices and some of the edges, so that the spanning tree's total value, adding up all the edges in the spanning tree, is minimum. No other spanning tree can give a better answer. So for example, if we have this graph, so it's, I guess a couple of ways, maybe a couple of ways we could approach this, but what would be one way to do this? One way to start finding minimum spanning trees. So for example, we have this edge of weight 5. Would we want to put that in our answer tree, or is there a reason why we wouldn't want to put that in our tree?
Because one part is lesser value instead of 5.
Yeah, so for example, and just a couple of thoughts we want to get. If for some reason, out of all the edges on this cycle right here, we wouldn't want to add them all, because one would be overkill, one would be too much. We want to get rid of one of them. And chances are, and all the other edges would have to be in our graph. So, on this cycle, the one we don't want is that one. That would be the most expensive one. If we had to get rid of one of these, that would be the one we'd want to get rid of. So it might be a good idea to start with the smallest edge as a starting point. We could make the argument that we'll never be able to get rid of it, because the only way to take it out of our answer, we'd have to have some other edge that's bigger than it to join. Because for example, if E and F are not on a cycle and this edge is part of our answer graph, and then we got rid of it, then these two would be disconnected, so we'd have to find some other edge to get E and F to be reconnected again, and that other edge would be more than one. So we can make the argument that this one would have to be in our minimum spanning tree. So we add that to our answer, so we're slowly building our answer. Now the next thing we'd want to look at is, there's a couple of choices, a couple of ways to go. Would we be looking at only edges connected to these two, or would we look at the whole graph and just start picking out the smallest ones that are still not added to our answer? So what we could do is take the next smallest one, and it's actually two, it's a tie, this one and this one, and I guess they're tied, so we can randomly pick one. So we'll take this one and add this to our answer. And then our third one, we would have this one, this is the next one in smallest to largest order, we'd add this to our answer. Then the next one after that would be this one. And I was kind of hoping there would be a cycle along the way. There will be one. Okay, after we add this edge to our minimum spanning tree, we do not have this edge in our graph. Suppose hypothetically, I'd have been good if this was a 4 also. If we were to consider this, we're going to look at this 4 and this 4 and pick one of them. But suppose this was a 4, would we be interested in adding that to our graph? And why or why not? Right, this would have caused a cycle. So even if it was a 4, and it was considered one of the ones we might add to it, we're not interested in it because all of these vertices are all connected together, and this just makes these join together, but they're already joined together. So then we would pick, any one of these two, and now we have found a minimum spanning tree. So the idea of taking a graph, taking all the edge weights, and I guess we have to sort them from smallest to highest, then go through them in sorted order, and keep adding the smallest one to our answer. But it would have to be under the condition that by adding it, we're not creating a cycle, because that's just an edge we don't need. So we'll skip the ones that would cause a cycle until we get to the very end. And then our algorithm is finished. So this is a famous algorithm. So somebody named Kruskel gets credit for this one. So it's Kruskel's algorithm for finding the minimum spanning tree. So we take a graph as input, and then what we're going to do is we want to make sure that when we are considering adding an edge, for example, if we were considering adding this one, we want to make sure that we're not creating a cycle. That means we don't need the edge. So every time we consider adding an edge, we have to ask ourselves, will this cause a cycle? And if the answer is no, then we'll add it. If the answer is yes, we'll skip it. So what we're going to do is we're going to say for every vertex, we're going to turn it into a set. And so the idea is if we're considering an edge between two vertices, we could ask ourselves, are those two in the same set? And if they are, that means they're already connected to each other, and this new edge is pointless to add. So first we're going to make a set out of everything, out of every vertex. So every vertex will be its own personal set. And then when we start adding edges, those sets will get merged together. Then we're going to sort all the edges by smallest to highest weight. And then what we're going to do is we're going to go through each edge in the graph. We're going to say if the two endpoints, the endpoint U and V, if they are from different sets, then this edge will not cause a cycle to be added to the graph. And therefore, we could add it to our answer. The way we add it to our answer, A is our answer graph. We take that edge and add it to our already existing sets. And then we call this union operation, which is saying take the set that U is from and take the set that V is from and turn them into one big set. So the idea of the set would go like this. So we would initially, so the way this one worked, initially our sets are six separate variables. And the first vertex that we added, the first vertex that we added was the vertex connecting E to F. So originally all 6 points were in separate sets. We decided to add the edge between E and F, so we have to make E and F join as a set. Somehow join them. So we could pick any of the collections and throw them in an array, or somehow join them together. Then we had to take C and D and join them into a set. And then we had to take the set that E and F belong to and add A to that set, and so on. So one of the most important things we're going to do with this algorithm is this operation, find set, and we're going to call it 2 times. We're going to say to U, the vertex U, we're going to say, what set are you from? It's going to give us an answer. I'm from set number 3 or something. We're going to say to V, what set are you from? I'm from set number 5. Oh, okay, so then they're from different sets, so we'll add that edge. We would like this answer to come out as quickly as possible. So what we're going to do is use a heap, which is a kind of a disorganized pile of data. So at first, the first set is up here. The first set is all the vertices are separate. When E and F became a set, we said, all right, we'll have F point at E. So kind of like F is the parent of E, you could think of it like that. Then A was added, A was merged into F, so A was pointing at F, which is pointing at E. So if we ever said to the vertex A, what set are you from? It would follow its parent pointer until there's no more parents. A would belong to F, the set that F is in, and F would belong to the set that E is in, and then so A and F and E all belong to the set E. Then we added the vertex C. C was connected to F. So we made C point to F, or C is a child of F. So now if we ask C, what set are you from? It would go, C would look at its parent, which is F, which would look at its parent, which is E, and then E has no further parents, so C belongs to the set E. And we do that so on, until eventually we had our sets like this. So at this point, every vertex belongs to the same set. Every vertex belongs to the set E at this point. So when we went to consider adding, that won't be the next edge we would consider adding after we were done. If we went to consider adding the vertex, the only two edges we're not considering are 4 and 5. If we said, let's see, should we add the edge between A and B, we would ask, what set is A from and what set is B from? And at this point, A would come from the set E, and B would come from set E. They both be from the same set, so we won't add that one. So now the question is, what is the running time to figure out what set you're in? And it would be like climbing up a pile, like a heap, which would be log the number of vertices. So that's a lot better. Go back to the algorithm. That would be a lot better than putting these sets in a linear list, because then you'd have to go through every list instead of walking up a tree. So the running time of Kruskel's algorithm, the first step, where we're making all the vertices and turning them into independent sets, that takes a running time proportional to B. The second step, where we sort the edges from smallest to highest, would take, well, whatever sorting algorithm you use. So we could use any of the n log n algorithms. So since we're sorting them by edges, that would be an E log E algorithm. The third step is a little bit convoluted in that the third step is, lines 5, 6, 7, and 8. The third step is that for every edge in our graph, so that's going to be E times something, whatever goes on here. For every edge in this graph, to find out what set they're in, this function, since we decided to use a heap, will take log B, and this step will take log B, so there'll be 2 of those. Adding something to our answer would be a constant time operation, and the union would be also a constant time operation. So for example, well, this example didn't have a good one like that, but when we decided to add A to this set, we knew that A was its own root, and we knew that it was being merged into F, so we just pointed A to point at F, so that would just be a constant time operation to merge them together. What we'd also have to keep is maybe an array of pointers to where these all are, because if we ask the question, what set do you belong to, we have to start off by going to B and then follow the parent pointer to the top of how do we get to B, so we'd have to keep some kind of reference to B, so that we could find it in constant time. So, the overall algorithm, the third step, would then say, for every edge that we're going through, each one, we do the find step, which is log E 2 times, to find the edge, to find the group that it's in, to see if it's in a cycle or not. So if we decided to represent that as using heaps, the second step would be E log E also. I'm sorry, the third step would be E log E also. So the whole algorithm could run in E log E. Okay, yeah, then the argument on the correctness of the algorithm, does this algorithm always produce the correct answer? And it's an inductive argument, so it's basically saying we start off with an empty tree, so that would obviously be less than the minimum spanning tree if there's no edges. And we repeatedly add edges to the graph, as long as it meets the condition that it's the smallest edge or tied with the smallest edge of all the ones being considered. And that by adding it, we're not causing a cycle to be made. So every edge we add will make the new graph, the new answer graph, as we're slowly building it, always have a weight less than the minimum spanning tree, and we will never create a cycle. So it'll always produce the correct answer. Okay. Another algorithm, I don't know if this, it's just a different way of looking at the question, but we're picking a vertex and saying what's the smallest edge connected to it. And then saying, okay, let's add that edge, and then say out of the two vertices in our graph, D and F, what's the smallest edge connected to this one? So we're basically, instead of like Kruskel's algorithm where we're randomly adding smallest edges until they all form a minimum spanning tree, in this case, we're going to be starting with a particular vertex, adding the edge that's smallest to that graph, and now say with this graph, what are all the smallest edges, which would be, we would consider the 5, the 3, and the 2, and take the smallest one out of those three choices, add that, and now out of the 5, the 3, and the 4, we would take the smallest choice, which would be this one. And now that this point has been added, we take the 2, we're also now considering this 2 and this 4. So the next edge to add to this graph is the 2, the 4, the 5, or the 4, whichever is smallest. And we would add the 2, and this was already one of our choices. And now we could pick either one of the 4, the 4, and the 5. We take the smallest of all those choices. So we have a tie, so we could pick either one of the 4s. So Kruskels is randomly adding edges from smallest to largest until you finally have a minimum spanning tree. Prim's algorithm is starting with a certain vertex, add the smallest edge that's connected to that one, and then that will bring in a new edge which has a couple of more edges to choose from, and again, pick the smallest one. So with this algorithm, what is something we're going to, at each step, what is something that's going to happen to all our edges? So for example, when we added the E and the F edge, so let's say for example we started with at the F edge. So our choices were the edge of size 1, 3, and 2. We would pick the smallest edge and add that to our graph. This edge of 5 wasn't even connected to F. So maybe maybe this edge was considered, infinity away. So now we add this edge, now D is considered 5 away. So the distance D is from our graph went from like infinity down to 5 and became one of our nominees, a nominee for the next edge. But we also had other edges. And if this one doesn't beat one of those, we wouldn't pick it. So we need a data structure that we're going to add stuff to, but could also tell us out of all the stuff we've added, what's the smallest one so far? And what would be a good data structure for that? So we're going to be doing a lot of adding, and then we're also going to be asking the question, what's the smallest out of all the stuff we added? So we need a data structure that's pretty quick to add to, and pretty quick to answer the question, out of all the stuff in the structure, what's the smallest one? What would be a good data structure for that? So a min heap, right? We've done max heaps when we did sorting using heaps, so we'll choose a min heap for that. And so Prim's algorithm is basically, we're gonna copy the graph over to Q, and then for each vertex in Q, we're going to say its distance from the minimum spanning tree that we're building is initially infinity, and then we pick a particular vertex, we'll call it root, and say that is 0 away from itself. And we can also, as a side statistic, if we want to do side problems, we can keep this vector pi as the author of our textbook uses pi to mean who is your parent, what node were you connected to when you were brought into this graph. Okay, so then as long as there are vertices in Q, we need to extract the smallest one, and then say for everything that the new edge or the new vertex is connected to, those numbers may become smaller. They may become new nominees that we would pick. So for every vertex that is adjacent to the one we just picked, for every one of those, if that vertex has a better weight value than the one we already knew about, then it's kind of like the relax method in Dijkstra's algorithm. We'll record them as their parent and record their new, now smaller weight. So that would be the step like this. So the step where, let's say, the step where we were considering, we were at this graph, our choices were the 5, the 3, and the 4, and we decided to add the 3. By adding the 3, we now say, okay, this point C has been added to our answer. Take every point it's adjacent to, which is now the B and the D, and take this number 2 and this number 4, and push those into our data structure so that it could then answer that 2 is the next best answer. So 2 would now beat out our current nominees of 5 and 4. Okay, so that's Prim's algorithm. So basically, we're extracting the smallest one out of our set Q, and then for every vertex that U ends up being connected to V, V is the new point that's being added. So we take every edge adjacent to it and say if that one has a better number, let's add that to our algorithm. Okay. So yeah, again, so the running time of this algorithm is the first step, which is line 2. That's where we're copying all the edges of all the vertices. No, all the edges over. No, sorry, all the vertices over. That would take order B. Lines 3 and 4 is where lines 3 and 4 is where we are saying every vertex is infinity away from our answer. That takes order V. Picking one element as the root and saying that we're going to start with that takes constant time. And then the loop 5 through 12 is basically, okay, the extract min operation, say out of all the objects in our data structure, give me the smallest one. To pull that one out, we then have to bring the new smallest one up to the top. So that would take order, using a binary heap, the total number of times that the loop 9 would execute would be 2 times E. So for every edge, it would be, for every edge that's added, 2 vertices could be put in. So, so 2 times E is also order E, right? The constant 2 would go away. Okay, and then we can keep a bit for each vertex that tells us whether it is in Q or not. So a bit saying yes, it's on or not. So that test would take constant time. And then by choosing a heap, the extract min operation would run log V. So that loop ends up being executed V times. So the extract min, which has 2 steps to it, each taking log V, will run V times. Okay. So there's really 2 major components to the algorithm. One that's running V log V, and another one that's running E log V. And then, again, from graph theory, if a graph is fully connected, which a lot of times these algorithms will be, you'll have a network, a collection of all nodes that are all connected to each other, and maybe you need a spanning tree to make sure that you have, security that they'll definitely stay connected. So a lot of times the algorithms are going to be based on fully connected graphs. And so if the graph is fully connected, one of the properties of a graph like that is V is equal to 1 minus E. So then we could say the overall algorithm is E log V. Okay, and yeah, so that's the running time of Prim's algorithm. So basically there's not a lot of difference between the two. And what do you think is the major difference between the 2 algorithms? What's that? Yeah, it's really, right, so in the end, we're gonna produce a minimum spanning tree. As we said earlier, a graph could have multiple minimum spanning trees. This is just gonna get one of them. But yeah, it's really, so both algorithms use the principle that we are picking the smallest of all the possible choices. We're never adding an edge that's gonna create a cycle. And the idea of picking the smallest one is they're both using the principle that if there was a cycle in the graph, you would always pick the largest edge in that cycle and then remove that edge to get to a spanning tree for that cycle. And they're both doing that. So just really the order in which the edges are added to the graph, they're both added in smallest to largest so that you don't create a cycle. And the order in which they're added is a little bit different. So suppose you were given a question where you were given a graph, then you computed the minimum spanning tree. Maybe you used Prim's algorithm, maybe you used Kruskel's algorithm. You computed the minimum spanning tree, and then one of the edges changed in value. So is it possible that your minimum spanning tree is now not the minimum spanning tree? What would what change in value would cause you to possibly not have the correct answer anymore? Like if an edge went up in value or down in value, or could? Yeah, okay, so what's the case where an edge from the original graph went up in value? How could that make your answer now not correct?
Probably there's an edge which we didn't pick, which was lesser than the edge.
If an edge went up in value, that would mean we picked it,
Yeah.
but now it's so high, maybe we shouldn't have picked it. So if that was, so there's really two scenarios, right? One is, you say both cases. If an edge went up that is in our answer, we might want to get rid of it. And if another edge went down that wasn't in our answer, we might want it. Okay, so the first case, if an edge goes up from the original graph, one thing we can do is rerun the whole algorithm, but is there a quicker algorithm to get to the, we're almost there. We have almost the minimum spanning tree, except one edge went up in value. Is there any quicker way than rerunning the whole algorithm all over again? We could look at all the edges the edge that went up in value, find a cycle that edge is on, and just run around the cycle and kick out the largest. Wait, that would be one went up in value. So that's one we had in our answer, we might want to get rid of. So yeah, we run around the whole cycle looking for a better choice, and then if whatever the best one is, replace it with that one, and then we'd be done. So yeah, so algorithms that find cycles in a graph have a running time of order V, so that would be better than recomputing the whole minimum spanning tree. And then the other case where one edge went down in value, if we didn't include that in our answer, we now may want to. So we would take that edge, add it to our minimum spanning tree, which would cause a cycle, and then run around that cycle and look for the biggest edge and kick that edge out. So yeah, so the little like side questions that might not make sense to go and redo the whole algorithm over. It might be good to just run the algorithm that just finds a cycle in the graph. So if we wanted to find a cycle in a graph as quickly as possible, how can we do that? Just a cycle, not based on the biggest cycle or something like that. Just can you find a cycle in the graph? So we could run breadth first search or depth first search and have it run until it visits a node that it already visited, and then we know we hit a cycle. And we could keep a list of all the edges that got us to that path. So we could go through that cycle and kick out the biggest edge or the smallest edge.